mean, in the power system dynamics, stability, control, and optimization, this is a very old topic, and you will see a lot of topics are old, but we have a new twist, and I'm trying to explain basically what is that new dimension to the problem itself. So, for example, in the power system, there's a lot of renewable energies are integrated, right? There's like basically wind, there's solar, and then you have batteries, you can store these things. The question is, how can you maintain the health of grid without going to the failure mode? And then how can you control this? For example, check stability first, and then if there's a problem, can you control it? And then can you optimize, for example, sustainability for other measures? Regarding the demand-driven production, I explained all of the discrete production planning. So there's a process control aspect of that, so those are all topics of interest. And basically, this is the path that I'm driving. Basically, data-driven control and resource control. So what we do is control identification, optimization, reinforcement learning. That's a huge topic. I'm aware of that. But what we are looking for actually the synergies with the other groups, and also other application areas. So, for example, if there are actually many examples in the power systems where we can integrate data into the model, or maybe learn from it. So that's what we do in some of the applications. There's also in the planning, for example, you can actually optimize your things with the trees, search trees, etc. But the question is, can you also get a surrogate search path with the data? And that's basically what we are working on as well. So regarding the data-driven control, we also have a standalone dimensions complementary to the power systems and basically demand-driven production. We are also interested in mobile platforms, small platforms, for example, like microchips and things of in that nature. Also, we have a design aspect that I'm going to talk about. Like we are using basically data-driven approaches to get a better design, and I'll go into that. So the overlook is something like this. Basically, I'm going to give you a landscape on data-driven control. That's completely from my perspective. By all means, exhaustive about the data-driven control at all. Basically what I'm doing, and then I limited that into the 5 years to give you like a reasonable chunk. And then a closer look on the basically multi-objective reinforcement learning, a little bit closer look on the architecture discovery, and I'm going to go into more detail on that. And then I'm going to summarize a little bit the outlook, what we are thinking, what is out on the horizon, what we are thinking to progress further in the maybe 4 or 5 years. So regarding the landscape on data-driven control, I'm going to basically touch upon like what are the challenges and what type of solutions we provided there, just scratching the surface, just to give you an idea about like what's going on in general. So it's not like a closer look type of section where we go really deep. And here I'm going to try to position them as a small scale, medium scale, and large scale in some sense, like how big the application is. And also in terms of like their expertise domain, for example, it's about modeling, it's about control and learning, and software and edge. And I want to just make a clarification here. When I mention about software, it's commercial software. It's not about like some repos, etc. It's something you can sell to your customers. And then edge here is basically it's important that it's not connected directly to the cloud. So because in manufacturing, data privacy is utmost important, so it's going to be a problem if you basically upload to the cloud, so it has to be inside the factory level. Factory level can have actually smaller cloud if they need to, but it's a self-contained area. That's the major thing. So let's start with this one. Essentially, it's a mobile platform, so you have, this is an Intel Minimoard Max mobile platform, and the right one is Moto X. So essentially what we did here is, you get a lot of like the things to show in the images, etc. in the phone, right? And then the question is, you need to set, for example, a frequency of the GPU to basically operate on. And then each frequency basically has a cost. I mean, it has like if you clock the frequency high, then it consumes a lot of power. If less, then you wait a lot, etc. So an important piece here is, can we have like some frame time prediction, right? Like frame time prediction, essentially like looking at the counters of all your GPUs, right? The question is, looking at those data, can you predict how much this is going to take to process? You know, because if you know that, then you can find the right frequency level, and then you can tune basically GPU for that. And here, what we did is a very systematic approach. Basically, you have a lot of available data to you through the counters, the feature, a lot of features there. What we did is a standard like feature selection, essentially which ones are more relevant to the basically the output of the GPU performance in terms of frame time. And then we did also the online learning with that. And the reason is, you know, like the data is changing in nature. For example, you're playing a game, you know, the frames are, you know, like coming in and you're trying to show, but you open another game, and then that dynamic is a little bit different. So you need to have some adaptability there. And then that's where this online learning happening. And then if you basically use this model to optimize your energy saving, then you can get a serious improvement on the energy saving. Another one is power temperature prediction on mobile platforms. And why this would be interesting, because I mean, I'm sure a lot of people notice here, you know, you hold it and then it becomes like hot, you know, somehow, or in the laptops actually this happens more often. And the question is there a way, you know, like by looking at actually how these power consumptions are set up, and then understand what will be the temperature, you know, for example, 5 minutes from now, can we estimate actually the power versus temperature distribution? Is that possible? And then what we did here, there is basically a theoretical analysis of the power temperature dynamics. It's a nonlinear evolving equation. And then the most interesting part is actually we validated when actually the predicted temperature is whether it's achieved or not, you know, after a certain time experimentally. So that's actually like the theory is on the one side, but at the same time whether we can really predict on the machine itself, on the platform itself. And then once you know that, right, once you can foresee actually the modeling aspect, you can immediately use that in the basically cooling process, right? Because if you can immediately see that it's going to heat up a lot, then you can say, oh, maybe I should take it from this processor to put a smaller processor, and that's not working yet, so we can basically use that. Of course, there's all these dilemmas, right? Like basically in the higher power full process, it's going to speed up, like work really fast. But when it's speed up, then there's a danger of actually deteriorating, etc. So the question is, then you cannot use that anymore. So when you need to transfer, for example, one application to another, and that decision based on basically the temperature profile. Because if you can afford it, go for it. You can just run it, right? But if you cannot, then which application and how you need to basically transfer. And that's basically the application where terminal management algorithm happens. And that's basically trying to kind of hint, you know, if you use, for example, a TD mark application and then somebody else is opening another application, then actually you can see that it heats up quite a lot. And then the question is, like, you can still control this thing, although your application is running both. You know, you're still serving, but it's just, you know, reutilization of the source based on the thermal profile. Another one is, this is trading of time and power real time on domain-specific system on a chips, right? So here, basically, you have like a bunch of CPUs, GPUs, you know, it's for more portable application. What we did here is, there are a couple of actually requirements here, I think quite interesting. One thing, these things do not run like a neural network, like big things. So it needs to be really lean. And the reason is we want the inference in the order of nanoseconds, and that's actually quite small. Even actually in the control, it's millisecond level, so nanoseconds is very speed up. So the question is, how are you going to do that? Of course, the idea was like, well, maybe you can use like a decision tree type of thing, you know, which is very easy to evaluate. But then, the thing is, we need to basically have a differentiable one, basically to train with the reinforcement learning. We want to basically simulate a lot of things, and then basically learn the decision tree based on that. But the tricky part is, we want to basically trade off this thing online. So when I say online, you want to trade off in the nanosecond level. So there is not much time to compute actually here. Basically what you need to do is you can define your trade-off, and then the policy or whatever algorithm needs to do this trade-off needs to immediately basically give the output for that trade-off. And I think that's what makes this a little bit interesting. Essentially, you can train a differentiable decision tree based on the Pareto front, right? Pareto front of different trades-off, right? And then the question is, like, if you can actually learn all these like different trade-offs on a single decision tree, then while you are running these things, depending on your trade-off, you can just set up your trade-offs, and then the decision tree will basically adapt to that. And it's not going to be a recompute. It will basically output the right actions for all these different weights of the trade-offs. Okay, so that's what I want. That's the reason actually why I have the plot. So essentially these are like the more mobile platform things, and they are like mostly small scale. And I showed you some of the things, a little bit just of the modeling aspect, like how we model things. And also we applied these models to the control and learning, and then how can we optimize, for example, the power thermal thing, or maybe in terms of the processing time, we basically apply to that. Right. I mean, the Mentor graphics are interested. Mentor is actually one of the big branch, right? They're interested in this chip design, etc. So they are always interested in like what type of tools we can develop for the people, and this is our like prototypical example, right? Like basically, if you have a phone customer, and then you're gonna like analyze, for example, power, temperature. How can we do that? So this is our proof of concept, and that's what we do in Siemens technology mostly. We work on proof of concept. Right? I mean, what do you mean by environmental conditions? Right. Right. Yeah, I mean here, for example, one example for the power temperature, a lot of design is based on the sensor measurements from outside. So essentially, when we actually design this, it's not like a lab environment. Like, I mean, Moto X is literally somebody is using it, right? And then we are testing basically whether it works or not. So it's not, in the mobile application, it's not that different actually, whether it's from the different place or, but that's a good point. Yeah, I mean, you need to basically test that the simulation or maybe research to real environment is important or not. Yeah. For this one, basically, this is a wearable device. There is a Siemens Healthineers, right? Like they are very interested in actually how we can embed these smart device into the maybe health, into life, etc. So this one is a prototypical example, essentially. What it does is it can do some computations, right? Like kind of like a smart watch type of functionality. It can measure some stuff, right? But the critical part here is if you actually move this thing, it actually also harvests energy. And one of the reasons we are interested in this thing is everybody, I think, complains about the battery time of their stuff. So the question is, like, if we can provide some functionality to you, can we provide it like free in terms of energy? Like, is that even possible? Like, let's say it's showing some time, etc., but we don't basically help them. Can it sustain itself? But in order to do that, then you need to basically kind of trade off between utilization and battery energy level, because if you don't have, for example, enough energy, you cannot do fancy stuff. Maybe you need to hold off, right? Or maybe you need to tell the people like, well, you need to recharge me now immediately because you didn't run enough or you didn't move enough. I don't know. I'm sitting here maybe a couple of weeks, so there's no hope. That kind of indication is needed. But if the life is regular, let's say, I'm not saying I'm like that if you're exercising, etc. But the question is, can we understand, for example, when you guys are exercising, like every night, or like when, and then depending on that time, can we distribute basically our computation across your daily life? You know, like for example, let's say you are exercising at a certain hour, can I put my computation mostly there because there will be a surplus of energy, I cannot store it, but then I can compute it. I mean, if I can, because the energy is there, right? So those type of trades-offs. And you can see that actually, that's why I chose to give the presentation, the closer presentation on the multi-objective reinforcement learning. The reason is this multi-objective nature is a very, very important problem. And I actually tried to, talk with a lot of people. It seems like they have, like a lot of people are thinking, it's a niche topic, it's not. It's actually very fundamental because a lot of cases people are doing one objective, one remote, whatever that thing is. But in any reasonable industrial design, you will have many. I mean, 2, 3, if you can 10, sure, whatever. But the question is, that's why this more will appear in a lot of trades-off, right? So here what we did is, basically you can collect a lot of data, right, about like basically different utilization and different power level, etc. Like you can essentially learn the Pareto front as a neural network of this device. So what that means is, again, I'm going back to basically what I tried to convey before. You have a function. I mean, it doesn't have to be neural network. It was a decision tree, by the way, before. So you can trade off their weights, right? And then it basically adapts its how to act, right? Like it's kind of embedded in that device. If you have that, right? So you can use this approximate dynamic programming, which is basically kind of like an MPC, but what it does is on the horizon, it tries to optimize like the next 10 or 20 or 50 steps. In this particular case, it's a day. You try to optimize it for a day. And the question is, if you have this oracle as a more, right? If you have that oracle, then you can use that oracle and say that, okay, if this guy is doing this and this is this, how should I basically behave in terms of the trade-off? And if he's behind this, and this is all uncertain because we cannot predict what you're going to do next. I mean, it can change. Maybe you change your mind. You don't want to do exercise, right? But the question is, with this oracle, you can actually create a lot of these rollouts and then find the aggregated best policy to trade off these things. Again, that falls into like the control learning and the medium, not the small scale devices, right? This is an interesting one. I want to actually talk a little bit about this one. I'm not sure how actually frequent that is, but essentially this is a new paradigm at Siemens we have. So we can now, with the computational power, create many designs. So as a concrete example, for example, you have a hybrid electrical vehicle, right? And then the question becomes like, okay, I can give you like 2 diesel engines, 4 electrical drive, and then like 2 batteries if you want to. If you don't, that's fine. The question is like, how do you want to connect these things? Like, is there any advantage actually in terms of, for example, fuel consumption, depending on what your requirements are, obviously. But like, or is it a high performance one? Like, how are you going to do that? It is all back in front, two. Like, how are you going to do these things, right? And then this generative engineering basically allows you to. This is a software, commercial software. Basically, you can define each component, right? And then this SAT solver basically incorporates your basically constraints and everything, right? And then it generates all these designs. So you can, for example, have maybe 1,000 designs, right? Like all are feasible within the constraints, right? So that's not super new. But the question is, somebody needs to tune those. That part is, I believe, a little bit normal. Because the reason is, when you, for example, talk about like, like a lot of like these design problems, a lot of people jump immediately. Okay, I'm materialist design, I simulate this, right, and then it gives you a successful response, so this is a good design. But for a badly tuned system or a goodly tuned system, the simulation results can be completely different. It could be a very nicely tracking system, or it could be a highly oscillating system. And the only difference is how are you going to tune this thing, right? So that kind of my work actually comes into the picture. So this is another thing actually I realized. So when you talk with their customers, or also like the people who are providing these models, you tell them, for example, okay, can you give me like all these like equations? If you know, well, can you provide at least a linearization of it? No, I mean, because the thing is, their models, some of them are black box. Some of them are like crazy stuff, you know, like they are using some FEM solvers, you know, obtaining from that, etc. I mean, believe me, these tool chain is not as smooth as you may think. So the question is, it boils down to what can you do, right? And the question is, well, if you actually give us like an inputs and outputs, we can simulate. We can give you the output. Okay, so then it becomes like, okay, maybe we should more go to like these data-driven approaches. Then the question is like, can we like simulate, and parallelize and all these stuff, right? And then tune these controls, right? So couple work on that direction. Basically, we did with the DARPA SDCTS, which is Symbol Design for Cyber Physical Systems. Essentially, there is very similar. You have a UAV, a lot of components you can change. You need to tune them basically, you know, in automatic fashion, and that kind of like summarizes what it does. And then this is actually the marine version of that. Essentially, here a lot of teams are working on how to build this unmanned ship. And why, you may ask? I mean, because if you have an unmanned ship, you can actually throw a lot of redundancies, and that makes actually a very good ship design. For example, if humans are living, they need to breathing space. Actually, it cannot be too cold. You need a heating system, etc. But if you have unmanned, nobody cares. It can be like, I don't know, minus whatever the temperature, and it's going to be still fine. And then the question is like all these design, like can you control this in a systematic way, etc. So this is the HEP example. These are like the more like government project, which also gives you like a glimpse that, you know, at the Siemens technology, we do these type of things, you know, with the government agencies. We pair up with the universities. I'm going to touch a little bit about that as well in the next slide. So we work with the government agencies on the research part. This is from the digital industries of Siemens. This is the product kind of glimpse of it. Essentially, these are the components, and you can see that you can define ports, and they're not colored because of for the fun. They have all different functionality and purposes. That's why they are labeled in, you know, different ways. So, for example, you cannot connect one to another, etc. And you can define all these constraints in a computer language way. So that's fine. So here, this is the I-8 hybrid electric sports car. Basically, our goal was, you know, having for all these different designs. And the question is, how can we fast tune this? You know, like what I mean is, even with the reinforcement learning, like let's say standard, you can tune whatever you give you them. Let's say you have this already, right? If you tune back to back, for example, it takes, for example, a month, right? The question is, can you come up with a smart transfer or whatever thing you can think of, and can you cut down that from month to hours? That's the interest, because that has a very big business value. Not in terms of like, oh, this is very fast, it's so cool. It's about, you can try more designs, for example. Because if it takes months, you're gonna say, how much time I'm gonna suffer. If it takes hours, then you're gonna say, maybe we should try 10,000. You know, maybe expand the horizon a little bit more. And that will be a good thing to do. So that's kind of what we worked on there. So here, obviously, the medium scale is a little bit misnomer here, because I'm talking about the medium scale per realized system. So it's a car, it's basically a ship, it's a UAV, it's relatively like smaller things, right? And here, it's the control and learning aspects in terms of the tuning, so that part is good. And the software aspect is, once we actually develop this proof of concept, and that's what we do in general, we create a repository, very well documented, very nicely written, very structured, etc. And then hand over to the Siemens business unit, digital industry in this particular case. They take over, and of course there are a lot of meetings about like, what is that, etc. And then what they do is they integrate this functionality in their product, and then possibly within 1 or 5 years, depending on their horizon, they basically sell this as a feature to their customers. And that's how basically you start from, you know, some DARPA project, some research, and then you go to do like a joint co-creation with the business unit, and then you go all the way to the product to the end customer. That's the journey. So this may not be too much interesting, but I hope I will make it so a little bit with the details. So here it's an HGV. I think everybody is doing it. So essentially it's following a track. And the question is, here, like, how can we do learning to control under limited sensors, changing conditions on edge devices, right? And when I talk about, this is not about control application. This is something else. Here, what we are trying to focus is how can we do edge design modular in the software level? And the question is, can we address, for example, reinforcement learning requirements on the edge devices? So the focus is actually on the edge, not on the control. And then this edge recurring theme will be over and over again. And then we actually had a chance to talk to a couple of faculties on that. They are well aware of that. I mean, essentially what happens is the paradigm, I'm going to upload to cloud, everything's going to work there, and then I'll get the beautiful results, and then I integrate whatever I need to do, is not going to work for manufacturers. Because in the industrial AI, if that materializes, and we are working for that, anything actually you want to upload to cloud, there's a privacy issue. So unless you guarantee 100% that it's not going to be, somehow seen or other people, they are never going to do that. And the question becomes is, I mean, that's the privacy aspect, right? And the second aspect is, a lot of people are interested in like this waterfall computational scheme instead of everything goes to cloud idea. And I'm actually advocate of that as well. So for example, if you get a sensor measurement from a device, and if you have an edge device nearby, like for some computational thing, even like a laptop, whatever, around there, like if you need to filter the noise, you don't want to upload to cloud. Why you just filter there, right? And or for example, if you can undersample it, right? Like you can have less sample. If you can detect, like if it's repeating all the same thing, then maybe you can just compactly represent that. So that type of steps actually was interest here. What we did is basically we run an online identification on this machine. Online identification in the sense that this is kind of like running down, up and down, going that. We are measuring this, how this behaves, and we are trying to extract a model out of it. And this is not about the HGV here, it's about the factory. I'll give you a use case. For example, HGV in the Amazon store, whatever, it's just moving around carrying thing, right? And the question is, if you know a little bit control, if I put, for example, a couple of like laptops on it, and if you drive this, that control parameters, and if I put a washer machine on that, and those are different. It has, and if you run the same parameter, it's going to be inefficient. It can be wobble, it can actually consume too much power, all these stuff. So the question is, why the online identification is important there is we want to basically understand where we are operating it, right? Like we can measure things. If with the current control, if we really slow down, the question is can we update those things, get a more reliable model and then learn basically from that in a data-driven way. But the more important thing is, can we do it on a very limited resources? For example, Raspberry Pi. We're not talking about NVIDIA, fancy, because the thing is, you're gonna sell these things, right? And they're gonna actually look at also the money, right? Like how much, because there are a lot of, although people might believe that they have huge amount of money, but there's a huge amount of industry market which actually sums up to a lot of money. They don't have too much budget. They want to integrate these things, and the question is, do you have any solution for them or not? So just saying that you get the expensive one may not work always. So that's a little bit on the software and edge, and then essentially a little bit control and the reinforcement learning piece. So this is, I mentioned about the power system branch in our group. That's a pretty big group actually. It's a lot, like 6-7 people. Time to time I actually collaborate with them in different topics. Essentially, I wanted to show you here because this is basically a model of the Hawaii power system model, right? The Hawaii island. So here, basically, you can measure some data, PMUs, you have some controllers where you can change the parameters of the governors, etc. in the power system. You have some wind farms, right? Some batteries actually installed, and then of course there are some solar panels, etc. What makes this interesting for us is, this is what they call is islanded grid. Islanded grid means there is no connection from the main side, or ideally you don't want to do that. The question is, can you sustain yourself without relying anything else with all you have here, right? Like basically you get these, you need to store, etc. It's not that easy a problem, because first of all you need to model this very reliably, right? I mean, just learning from data at this scale is impossible. You cannot do that. But then the question is, even if you have the model, you're going to be off. Then with the data, can you complement that, right? Like that's going to be an interesting piece. And the question is, all comes to the decision making. How much actually, when I produce something, needs to be saved? How much I'm going to be used? Yeah, all these decisions actually, like nowadays, is the big topic in the power system area. And we are trying to help the control and data-driven control type of problems in that focus. Here we are doing Hawaii, but the group actually did successful project before that. We did a project in Guantanamo Bay, and then we did actually before that in Germany, actually another city in Bavaria. So we worked on different projects in that case. So the goal is basically, as I summarized, reliable power system operation under renewable energies of the Hawaii Island system. So I just picked one basically work. There are others, a lot other stuff, but just to give you a little bit the research flavor of what's going on. So essentially we have the development of large-scale power system models. This is kind of our in-house model. We worked on it. And we basically identify the critical M- contingencies. And when you say M1, well, what is that, right? Basically, if you knock off something, and then if everything goes well, that's M-1. Because N is perfect, M-1, right? And essentially is like, how are you going to decide this? Maybe, for example, kicking out a couple of houses here is not important, right? But probably, if you kick out some of the batteries, yes, that's a big case probably. And then you do this analysis. Since you have the model, you actually query like different places, and then you do in a systematic way of like a list of contingencies. You say, okay, I need to be careful about this and provide a control solution if this happens, because I don't want to basically go into dark. That's the main idea. And then once you have these contingencies, that's basically my work comes into picture, because I need to optimize the control parameters of these contingencies. Remember, it's not one scenario, it's a lot of scenarios, maybe 100, 200, right? So you need to control actually across all. So imagine, for example, hypothetically, one contingency creates like oscillations, the other one is like a little bit less, etc. So you need to find a control parameters like as an aggregated envelope, which minimizes actually all these oscillations so that people at home didn't feel any flickering, etc. That's the idea. And then, of course, this is another group, actually OpenRT Technologies. So they actually do high fidelity EMP simulation. So we validate also on that. And another important thing here is now we are actually on the process of trying this on the island, which is a big thing for us, because it means like kind of connecting from all the way to papers, simulations, optimizations, and then hopefully on the field, if you can see that, that will be awesome. So that kind of addresses more like the large scale, and then modeling piece definitely was there, control and learning was definitely there too. So a little bit about what I didn't talk about. So essentially, one was this multi-objective reinforcement learning. There are a lot of like different things we did there. Multi-agent reinforcement learning also, we worked on it. And you may ask, like, multi-agents, like why do we care? If the scale is large, then basically you cannot design a single controller to control everything. So you need to define like a distributed control, if you're familiar with it. You kind of like define different agents, and then these agents in a collaborative way they are trying to control, and that's basically our interest, because you can, for example, model like, oh, maybe I'm going to control this area, and then that area, that area, that area, but they're going to handshake in between as well. So it's more like hierarchical way of looking at the control. This is quite new, quite excited topic, G-flow. It's one of the a hot topic in the machine learning community. Essentially, in the reinforcement learning, usually you two like take the actions and then you do these steps on the horizon, right? They are actually modeling these things as a flow, and then they are basically enforcing some flow conditions about the equilibrium, which basically boils down to the Bellman equations of the optimality. But long story short is, we want to basically make a discrete decisions, discrete optimizations in the power system. Should I turn on the battery? Should I, close the wind power? Those decisions, basically, we want to use AI and see and compare with our classical optimization method and see that whether we have an edge or not. And it's always not like one or another, by the way. And this is a very common mistake. People say, optimizations are so good. Why do you guys are doing? That's not about that. I mean, like, if you can, for example, predict the pattern of the optimization path, right? You can use that as an oracle and then search around it and then get a better optimization. It doesn't have to be basically replacing the old one. It can be empowering the old one as well. And that's what we are truly interested in. And parameter identification is another thing we talked, right? So basically, how can we identify the parameters in the frequency domain for large-scale systems, and then with the structured controller. So this is something exciting we are working on. And another thing is, can we complement the parameter values with the data and then get an uncertainty quantification level? And that's quite important for us, because the most important question is not actually what the values are, how certain you are. If you are very certain, if it's a good value, you're done. But if it's not, then you need to trade off, like whether that value is reliable or not, etc. So yeah. And there's another aspect, is explainable AI. Basically, a lot of customers and operators are coming to us and say, okay, this is great, neural network, awesome, but I have no idea what this does. And then we say, well, it does this, you just input, output that. And then they say, can you actually extract some rules, some ideas actually what this does in terms of like for this use case what it does, etc. But they don't give you the use case to simulate. It will be easy, then you will just run it. But then you kind of look at the neural network surface and say that, actually if you are in the operating region of this, these things happening, if this and this, and the very interesting thing is actually when you explain it, your results to that, usually the operator says, well, that makes sense. Because that region does this, a lot of you never understand, obviously. But then you say, oh, okay, you're doing that because it's fixing that piece, and then they make sense out of it, and that helps people to actually integrate their model into these things once they understand better. And the thing is, if they're not very comfortable, you can actually replace the neural network with the rules as well. So then basically you kind of solve the neural network problem. Of course, you need to validate the differences small, and then you can get similar performance. On the software level, there's a whole different reinforcement learning toolbox. Actually, we actually worked, and then we are still continuing to adding new features. For example, control for generative engineering is one piece of that. And here, the important part is basically we work with the software developers as the researchers. It's kind of like a cross-domain language you need to learn. I think if you go in the industry, that will be like a very common theme, because nobody knows when you say something, what that means, right? And then you will not also understand what they're saying. So essentially, oh, you're saying this to that, etc. You kind of match, and then that's the only way actually you can transfer your research to the application domain, by communicating properly, and that's kind of like what we did there. So, okay. Yeah, architecture discovery, I'm not going to dwell on that too much because I'm going to talk about it. And then we are working with the universities as well. So essentially, for example, this mobile platforms and wearables with UV Madison, we actually worked with them quite closely, had a lot of results. And then with G-Flow with the Princeton, basically, we're working with Ryan Adams there. And also with the architecture discovery with Virginia Tech, we actually worked with them. That was interesting work. Actually, for control for generative engineering, we had an intern from Rutgers. So essentially, we worked with them, and actually twice. So we are open. Let us know, right? If you're interested in internship, if you wanna basically do joint work on the DARPA or RPE, those type of companies you're interested in. So now, this is pretty much, like more or less my view, last 5 years of, what's going on in terms of research, what are the main things, etc. Now I want to basically move to the moral and then architecture discovery, a little more closer look. So, before dive in, I just want to make a disclaimer because, since I know there's a more, multi-object expert in the community, right? So basically, this is not, like the aim to basically beat the multi-objective algorithms in general. The goal is for the continuous type of control problem, like large space in the sense that like 16, 17, 20, etc., state space, right? And the actions are, for example, 10, 20. There was actually a very much difficulty to use reinforcement learning to actually control this multi-objective use cases in the robotics application and continuous application. And this work tries to address that problem. Basically, we are looking for problems. Can we actually find a multi-objective optimization problem, solution for this continuous space using reinforcement learning? Like, can we do that with the reinforcement learning? That's one piece, right? And the second piece is actually more important is a lot of methods have this, a solution for each point, and then you update that, right? What we are trying to provide here, and you also get a glimpse on the applications as well. One network, one policy, right? And you need to you learn how you can trade off on that policy, and then you don't need to recompute on the real time. That's one of the biggest requirements we have, because in a lot of like engineering applications, we want to trade off immediately. We don't want to basically do the relearning, etc. So that was another thing. This is basically the background work, right? It's published in the ICLR 23. So, essentially, we have a preference set, right? This is linearly, of course, appears here as a vector multiplication. This is your preference, and preference basically says, I value this one more to the other one. I'm trying to explain for the broader audience. Essentially, for example, if you have a time, if you have energy consumption, if you say, for example, 0.5, 0.5, you will say, okay, energy and time is like equal. If you say time is 1, energy is 0, I don't care how much I spent. I need to go there as soon as possible. So that's the trade-off, essentially, for the preference, right? And then here in the classical reinforcement learning, you have an environment, right? And then you have an agent. Environment basically sends you what are the states and how good you are performing with the reward. And agent says, okay, do this. It basically makes a decision, right? And then you kind of want to find the optimal state action value function. And essentially how it's defined is, I'm at a state, if I take this step, how good is it on the long run? Not on the short is easy, but the long run, like basically the overall objective. And that's the function basically provides you this information. And once you know that, this part, the right part, shows how you can expand that in the reinforcement learning setting to multi-objective setting. And where it's a natural extension, essentially you get again states, right? But then you have basically maybe multiple states if needed, but also multiple rewards, right? So basically you get multiple rewards, and then you put the action here, because again the action is 1, so you don't have many, basically you have multiple rewards because of multiple objectives, but you put the action. And then now the optimal state action value function can be represented as like basically in a coordinate-wise way, like basically for the one objective function, if you are a certain state, what will be the action, how good is that, and then you kind of expand that notion into the dimension. So obviously, all the interesting cases is completing objectives. If it's not completing, what are the problems? So most common approach is scalarization. So basically, what this does is instead of having basically like this multi-objective, you multiply this with like a fixed one, right? You find a policy, and then you fix another preference. You solve that one, and then for all these different variables, you have different policies, and then there are different flavors. You can like approximate, average, be in between them, etc. There are some tricks to basically cover the Pareto fault with that. But the main idea is essentially, having a fixed preference and then solving that. And then here, another version is M-1 constraints. What they do is they actually define a one objective and take all the M-1 as a constraint to that, and then solve the problem that way. So it's a little bit different. But then, of course, all these info will creep in, because if you put a constraint, then what will be the upper bound value, a lower bound value, you need to know the domain, etc. So it's not all rosy, so there are some difficulties there. Another one is multi-policies. Essentially, you train distributed single policies repeatedly or simultaneously. For example, here is evolutionary algorithm. So, then, but I mean, there are some careful treatment needed there. So because you have a Pareto front, okay, and you do like some individual policies, and then you need to find like how these transitions, and then the transition is not too bumpy because it's a control policy. You're trading off the weights, you're trading off the different state. So you need to be basically a little bit careful there. And then also there is a possibility of, depending on how the Pareto front is complicated, like how many policies are needed, etc. So those are also like some problems there. And this is the meta policy. It's kind of like learn what is best for general and refine on the spot idea. So essentially you learn the meta policy is like the policy for all, like it's an aggregated one. And then you find with each preference, and of course this requires retuning. So for example, whatever your application requires, you need to kind of like refine this on the spot. I mean, obviously, for example, the nanosecond level application, that's not gonna. For milliseconds, that's not gonna work. So then that's the question is like it all depends on your, I mean, these are all valid, right? I'm not criticizing one or another, but it depends on all the problem definitions, what type of restrictions you have, etc. So this is a little bit primitive, but just covering the grounds. The Pareto front essentially, like in the two objective case, you have objective 1, objective 2. Essentially, if you can like have a non-dominant point, that's the Pareto front. That's a great point. Basically, you cannot improve further. If you want to improve further, you need to trade off essentially, right? But if you are in the middle case, then basically there's always a better solution than you can go, and that's basically how we define the non-optimal point. And then here in this paper, basically we define this local common, right? These are all on the multi-objective structure is defined, so it's not new, it's not something we did. But essentially it's the hyperbolic definition. So here you need to kind of know your origin, where you're at, and that's not very restrictive in applications, usually you know that. And then the question is like whether this covers this underneath area, is it big enough or not? So is it covers in that sense? And the sparsity is basically like how uniformly these things are distributed. Like are they like the hyperbolic can be large, but I mean they may be basically like all like linked here and then like couple here, but then hyperbolic can be large, but the question is it's not sparse anymore. So you essentially what you want to do is you want to fairly represent as large area as possible, but also uniformly, as much as well spread out. So this is basically what we were suggesting. So essentially, when you have a solution on the Pareto front, right, like you define basically these preference vectors, right? But then the solution, the Q values for the individual coordinates may not align with them properly, right? So the question is like, they can be a little bit off here, and here, like they are like in a similar direction here. But I mean, there are cases actually like they are a little bit off. Like if you look at angle, the other one is that. So the question we were thinking about is like, can we actually guide the reinforcement learning algorithm for the directions that we want to go, like in that direction? But of course, there's a catch here, right? The question is, how are you going to find the solution, right? Because the solutions you need to solve the problem, and that's maybe the one maybe caveat in this work is essentially you need to solve this problem at certain number of points. At 2, you can fairly like 2, 3, 4, And the most important thing is this solutions doesn't have to be dense in the Pareto front. Like it doesn't have to track the Pareto front. It's more like it needs to convey which direction and how spread this thing is, right? To basically pull the reinforcement learning algorithm policy to that level. So here what we did is, okay, like once you detect these solutions, we can design an interpolator, right? And the whole purpose of this interpolator is if you give me a pair of the preference, that kind of like gives me a direction. It says, you know, it needs to be this direction. And the goal is that like here, it's 0, 1, right? And this is 0.5, 0.5. And if you have something, for example, like 0.8 and 0.2, you know, the question is like where it's going to reside, and then can we condition the Q algorithm to direct that point? Not the magnitude, but the direction. Because magnitude, these things could be quite misleading. The important part is the digression, then the trade-off between them. So as a summary, so we compute some key solutions. We normalize the solution space. You can see that it's like they are all fall into the 1, 0. So the stars, the solutions as well, whereas in the original one, they're not. So you normalize them. And then you fit a multi-dimensional interpolator. And that's pretty much it. And we basically apply this idea to do DDQN, the double deep Q network algorithm with the multi-objective version. So the important part is now I'm going to talk about the DDQN. But also I'm going to insert like where we made it a little bit different, where this new multi-objective piece comes into. So our goal is obtaining a single policy network. That's important. So not multiple across Pareto point, but just a single one, right? And then it needs to cover the entire preference space, right? So here, for example, the state vector is S, the preference vector is omega, we have this. Now, you know, there are n of these Q values for the n objective, and then A is basically the action space, and then n is the objective space dimension, right? So having these inputs and outputs, the question is, okay, let's minimize this, right? Like this loss, right? And then here, the D is basically experience replay buffer we sample from. So essentially, if you think about it, this part is nothing different than this. I mean, essentially, the only trick here is this and that. Because if I just, you know, black that out, it's just a DQN. But the tricky part is, first of all, your Q network parameterized in terms of your preference. That's what you want because you want to trade off on real time, right? And the question is, how are you going to basically create this experience replay buffer with this different preference vector? And that's basically the key part. So here, basically this is the target value. In the DQN, for example, if you have like a target value, you want to basically pull the Q network up towards that target value. In the normal one, basically in the DQN, it's R plus gamma Q S prime, max of A prime, basically Q of S prime A. So it's not this fancy thing, it's just maybe this piece, you know, with the parentheses here, right? But what this tries to do is actually a little bit interesting. So essentially what this does is, it's for each preference, let's say you sample, you have one preference, right? It kind of finds like the scalar value for that preference, right? And then it actually, for the same one, right? It's for the same one, it looks at actually the projected direction, right? Like basically the direction that needs to go, right? And then it kind of computes this cosine similarity, like how similar this scalar value is, like in terms of the direction to this one, right? Essentially as a vector. And the reason is, like, for all these preference vectors, like all these preference things, if you can actually compute the scalar values on the direction, the question is, can you move to basically the desired direction, right? One question would be, yeah, go ahead. Ah, really? Oh my God. Okay, so then the question, I need to speed up, sorry. So essentially, then the question becomes is like, well, yeah, but how can you rely on this? If it's wrong, what's going to happen, etc., right? The question is, we train, but once in a while we update actually our interpolator. So it's kind of like a moving interpolator type of algorithm, right? We did the hindsight experience of play. I'm going to ignore that. Maybe this is not going to be relevant. Basically, I was going over in detail actually how the algorithm works in detail. For the benchmark example, I can just quickly say, for example, if you have like a submarine, essentially, it's 0, 1, it just stays here because I don't want to waste energy. If you can waste energy and important, the collecting treasures, you are in the middle. If you are just interested in the collecting treasures, you can go all the way up. I mean, that's kind of like, but you see, when you are transitioning from here, there is no recompute. You just modify this, that's it. You just, in the episode, basically, you put 0, 1 or 0.5, 0.5, that's it. So this is kind of explains how this angle idea actually helps the accumulation on the Pareto front to spread like that. And that's, I think, the novelty. And I'm gonna skip this, but basically I wanna show you like something like this, because the reason is, this is truly shows actually, like if you set the preference in one way without recompute, it just stays and then it just moves and then it moves faster. So that's actually what we had in mind when we developed this initially for the industrial applications, basically like trading off on time. That was our intent. Yeah, I mean, another thing here is we also note that the number of parameters are less than the state of the art. Basically, we are designing a single policy with less number of parameters, and then it's actually covering the Pareto front. I mean, there could be edge cases, but that's our experience in the benchmark examples, right? And then the single method. Yeah. Should I skip that picture? Yeah, maybe. Maybe I just finish this outlook a little bit. Maybe that could be an interest to people. Regarding the applications, I was talking with Professor Özel as well. We are actually interested in, like more like these edge applications. That's important to us. And then also industrial AI. That's another big topic that we are interested in. In the modeling business is how to integrate the AI with the data collection and then enriching our existing model. That's like the one hit topic here. Regarding control and learning, obviously multi-objective, meta-learning, those things are important. But also, anything in the generative AI domain, that's an interest to us. And then regarding the software, anything on the metaverse, where you can simulate your digital twin, or basically you can simulate your process and then get early results before implementing. That's one of the important things. Regarding the edge, I briefly mentioned there, we want to compute but locally if possible, and then do a waterfall effect to make it more scalable. I think that's a wrap.
Thank you so much. We can take any questions.
I completely agree with your first comment that every engineering problem is practice is a multi-objective problem, and we pretend otherwise.
Exactly. That's my point.
But that being said, often you can prioritize the objectives.
Right.
And beyond 3, 4, you can set constraints. Your example, you said 2.
Yeah.
Did you work with 3, 4?
We worked on 3, but we didn't go beyond that.
Because the Pareto set is huge.
Exactly. Well, we worked on 3, but not go. But as you said, I mean, when you go through, the one thing we observed is when you go more, some of the objectives becomes actually similar. That also allows some, like collapse in the objectives I
You
mentioned.
can correlate.
Yes, exactly. Yeah.
One thing, just a thought, the Pareto set by itself assumes you have no knowledge of the relative importance of the objectives, where your preference set assumes you have complete knowledge. In practice, there is a compromise where you can maybe prioritize your objectives without defining a specific preference set.
That's interesting.
This is more important than this. How
Yeah.
much? Not sure.
Okay.
All right, thank you for the
Thanks a lot.
I think the follow-up question was pretty hard to say. As an extension to what you said about the multi-objective learning of like one thing, could it also include a feedback to the outcome? Like for example, say, oh no, it's very important to me that this is always secure, but then, oh, it's that costly, no, then it's not that important to do this. in order that you have like an understanding of the needed outcome and
Yeah.
achieve that.
I mean, top of my head, it could be an iterative nature, I guess, right? That once you have that like you can integrate it back, but more like fast adaptive way, we couldn't think about.
There are some aspects that the decision makers or problem implementers have to decide. For example, what's a reasonable methodology? How the preferences be?
Yes.
So, do you have any general approach to deciding anything mathematical, or is it
Yeah.
commentary?
Yeah. I mean, the thing is, I mean, I'm not saying that's not important. It is. But I think there's a much more bigger trend right now. I mean, especially if we can create all these designs and then look at actually what really they do, then we decided actually having an information based on that is actually much more informative. Because the thing is, there's there's a guessing game there, right? Like, what if you're not right, etc. The question is like, how can you parallelize this, optimize together, and then decide basically which one? That's usually the route we are taking.
Is there a transfer learning?
Yeah, heavily. Because the thing is, like, for example, I didn't mention here is that you're learning a Pareto, right? Like, you're sampling another, etc., right? But I mean, like, if you're doing it parallel, you're gonna like warm start all these things, right? Like, that's one of the things like we do immediately.
You mentioned some data-driven control, you do some forecasting. Based on the forecasting in the future, you can optimize it. And you mentioned a little bit about the parameter problems, uncertainty.
Yes.
So what is your current state of current solution from Siemens dealing with those forecasting uncertainty in your or your industry?
I mean, the thing is, like, I mean, classic system identification already has this like covariance definitions, etc. So that's fine. Like, if you have like more linear system, etc., you're defining that. I mean, there's this covariance like definition actually allows you how uncertain you are. Our main focus there was if you're designing a neural network, right? Like complementing that, kind of getting an uncertainty quantification out of that, and that was difficult because you of course you can train it like a distribution neural network. If you go that path, then you have this signals, etc. But we found, for example, this, I'm not sure whether you're familiar, but conformal prediction, for example, was actually one method that we found successful. Essentially, what you do is you train it like a neural network, right? And then with the conformal prediction actually kind of gives you this uncertainty level in the output. And then that is useful to us because in a lot of cases we have an already existing model, we train, etc. But then we want to complement the neural network, like how again get more high fidelity, right? But then the question becomes like, how are we going to aggregate this uncertainty level of the existing model with the neural network? And there basically we have this signals from the conformal prediction we can combine with the classical results and then get it off estimate.
So that is kind of the modeling part of uncertainty more from
Right. There is also data uncertainty as well, but I mean we are mostly interested in the model uncertainty.
Thank you.
Yeah.